Every day, when we switch on the lights, connect to the internet or commute to work, we are forming part of what are called complex systems. But to understand complex systems, we need to talk a bit about systems in general first. A system is a type of model we use to understand the world around us. In its essence, it is a group of parts called elements that function together to form a whole that is called the system. This very simple and abstract model can be used to describe a wide variety of things. Now, let's add complexity to this. Although there is no formal definition for it, we can understand complexity as a parameter. That is to say that it is a measurement of something. Firstly, it is a measurement of the number of elements within our system. This is intuitive to us. A society is more complex than a small group of friends as it has many more subsystems and elements interacting on various scales. Secondly, it is a measurement of the degree of connectivity within a system. When we have a low level of connections between elements within a system, we can describe it by simply describing the properties of the individual elements. But as we increase the connectivity, it is increasingly the relations between the elements that come to define the system. Thus, complex systems are typically modeled as networks that can capture and quantify this information about the relationships between the elements. Thirdly, adaptation. When elements become capable of adapting, their behavior over time can become increasingly complex. Thus, complex adaptive systems are often best modeled as the product of evolutionary dynamics that have shaped them over time, as opposed to the static analysis of their individual parts. The capacity of adaptation also means that elements can self-organize, limiting the need for centralized control and allowing for the emergence of organization from the bottom up, as individual elements can interact and synchronize to form patterns. Fourthly, complexity is also a measure of the degree of diversity between elements within a system. Again, the greater the diversity between the parts, the more complex and abstract our models will have to be to capture the underlying common features. So now we have an idea of what systems and complexity are. Let's put them together, starting with a system with a low level of complexity. An example of this might be a set of, say, 5 billiard balls on a table. There are quite few of them, they are all the same, they are all separate from each other, and they are incapable of adapting. If we input some energy into this system by, say, pushing one of the balls, the outcome to this event is directly proportional to the input and is predetermined by it. We can repeat the same action a million times and we will get the exact same results. We call this type of system a deterministic or linear system because we can draw a direct line between the cause and effect, that is, input and output to the system. Because linear systems are relatively easy to model and control, much of our modern science, engineering and management practices rest upon this type of linear understanding to the world. Okay, so now let's think about what happens when we turn up the complexity. Take an example of an ecosystem. Ecosystems typically have many elements or creatures. These creatures are diverse, interconnected, and capable of adaptation. Now let's add some input to this system. Say we build an industrial zone right next to it, emitting pollution. Given the ecosystem's capacity for adaptation, the result or output to this may well be negligible to us initially. So we continue expanding our industrial zone. At some point, the stress from this additional input will reach a critical tipping point, with some small additional input being able to propagate through the system, creating a phased transition as our ecosystem collapses. Thus, complex systems can exhibit both extraordinary robustness and extraordinary fragility, where some small event can have a large systemic effect, known popularly as the butterfly effect. The point to take away from this illustration is that complex systems are what is called non-linear, meaning unlike our original example with a billiard ball, cause and effect are no longer directly related. It is due to the fact that complex systems are non-linear and largely defined by their connections that make them unamenable to our traditional scientific methods of analysis that often rely upon linear models and a component-based description of the world. Thus, the area of complex systems has arisen over the past few decades as an alternative paradigm within science and engineering to deal with these non-linear systems by placing a greater emphasis upon the connections and relations between the elements. It currently represents a broad and diverse set of methods, primary among which is the use of computational modeling, where elements are given a simple set of rules that govern their behavior and are left to interact and evolve over time to see if relevant patterns will emerge. As the world we live in becomes increasingly interconnected and interdependent, the need for a greater capacity to model, design, and manage complex systems is making this area particularly relevant to the challenges we face in the 21st century.